Everybody okay? And now, if zeta and epsilon are small, we can commute the rotations, and obviously a rotation commutes with itself, so the two y rotations commute. So in the third line, then, I've taken the y operation, which is shown, hopefully, this pi over 2, and acted on this z rotation. So this is a rotation around the z-axis, and we can ask, if we rotate around z by 90 degrees, what do we get? And the right-hand rule would say that a rotation of z around the y-axis by 90 degrees is an x rotation. So I've made use of that here. And what I didn't show, I have the minus 90-degree rotation over on the other side. So the middle two, I can get rid of the two y rotations by acting on the two z rotations, and that was done. Seems to get stuck. To get to this, the line here, where now I have x's instead of the z's. And now I can make use of the same trick, act with this rotation matrix on the other side, and an x rotation turns a y rotation into a z rotation. And that brings me down to here. And here we can go on a page. And I keep playing the same trick. Now I move I've recombined the x pi over 2 and the x epsilon back to alpha to get the final result that my off-resonance 90-degree pulse looks like a z rotation by an angle zeta, and then the x rotation by the angle alpha, which is a little bit more than pi over 2, and then another z rotation by the angle zeta. And if I use some trig identities down here, if zeta is small, then tan zeta is approximately equal to zeta, and that lets me write the rotation angle as something that looks like a frequency times a time. Yikes. So since this looks like a frequency times a time here, I can think of the off-resonance rotation as being a little bit of a z rotation for some time delay, a rotation around x, and then another little z rotation. Yeah?
Maybe you have said it, but do you imply there that, and this is why it's not equal, that small rotations, like small angles like commute? Is that why it's approximate?
Yes. And there'd be an additional degree of approximation because I've approximated the tangent of theta.
But you swap the axis there, right? From the first to the second line, you have not only switched the order of rotation, but you have swapped the axis of the rotation, small rotations. So it's the same as in the same change, you change the rotation order. Not really, right? From the first to the second line.
From the first
to the second line, z becomes y, y becomes z. You basically swap the r z and the r y.
Ah,
Is it the
here.
same thing again? No, not really.
So these all commute. So I can move this one all the way over to here.
They almost commute, right?
Right,
Okay.
that's the approximation.
Okay.
So this one got moved all the way over to here. This one got moved into the center. So I've reoriented the 3 small rotations here. And that's so that when I act with the X pulse onto this Y rotation, I get another Z with the X moved into the center. Because I knew that at the end of the day I wanted ZXZ. And remember the other day we said that for small offsets, the phase angle that was acquired by the magnetization was almost linear with offset. And we could correct with a first order phase correction. If the phase is linear with offset, that means that the phase angle looks like it's proportional to omega times some time. And that's just what we see here. The Z rotation is the phase error. And in our approximation, it's linear. It wouldn't be linear forever. And our derivation doesn't tell us how far it's linear for. If we wanted to know how good an approximation this was, we would have to, for example, expand in Taylor series to second order and find out what the first non-commuting term was and decide when that term got large. Or we could rely on the numerical calculation that showed that this was, the linear approximation was pretty good as long as the offset was not larger than omega 1, the amplitude of the B1 field. Okay, so that's intended to be just an example of the kind of manipulations that one does. So now let's talk about an experiment. So what's the experiment going to be? The magnetization starts on the z-axis. We'll apply a 90-degree pulse. Turn off the B1 field once the magnetization rotates into the transverse plane. At that point, we can turn on the receiver. The magnetization vector starts to precess in the XY plane and relax away with T1 and T2 processes. But we'll record the signal. The signal, you all know, is called the free induction decay, and then we Fourier transform to get the spectrum. So the simplest experiment is a 90-degree pulse. In the simplest case, beta is 90, and phi, the phase angle, is x. So we have a 90-degree X pulse, and then we record the signal. So with luck, actually, can I do that here? Maybe. Let's start to run. So now we're looking down from the top. Looks like this isn't going to run. That's funny. Well, this was supposed to be an animation of that. You'll have to believe me. So when we get done with the Fourier transform, the result is complex. There's a real part, and the real spectrum, the equation is shown over here. And then the dispersive part that you frequently don't look at is shown here. And then if you've done NMR, you know that what you actually see is an admixture of these two signals. The lines look a little funny, and then you phase the spectrum in order to isolate the imaginary part away from the dispersive part. So again, mathematically, here's what happened. We started out with Z magnetization that we could represent as a vector, and then a 90-degree rotation which is represented then by this matrix. If we look back at earlier calculations, this is for an x rotation, and if it's 90 degrees, alpha would be pi over 2. So exactly 90-degree pulse, we get this matrix here. And then we just have to do the multiplication of the matrices. Maybe that was already done. Did I do it? Yes, so after the, well, I guess I picked a y pulse. So after the rotation by 90-degree y, we have x magnetization. And that matches our expectation. If my thumb is the pulse on y, my finger's on z, the rotation, a right-handed rotation, brings magnetization to the plus x axis. And the mathematics say I end up with a plus x vector, whose amplitude is m naught. And then the magnetization starts to precess. And when the magnetization rotates away from the x-axis, there'll be a phase angle, there will be omega t. The projection back onto the x-axis will be cosine omega t. And the magnetization will precess towards the plus y-axis, again with our right-handed rule. So the projection onto the plus y-axis will go as sine omega t. So here's the x magnetization. And then we just add in, there's the trig factor. I've just added in damping with R2. And here's the sine component on the y-axis. And then it's convenient mathematically for us to combine these two into a complex magnetization. Usually M plus, we could have picked M minus. That's just a convention that I'll usually pick M plus as what we detect. So M plus is the X magnetization plus I times the Y magnetization. And that's convenient because then the trig factors by Euler's law turn into a complex phase factor. So this is a nice compact expression. Internally in the spectrometer doesn't have any imaginary numbers. It just keeps the real component of the free induction decay in one set of memory locations and the Y component in another set of memory locations, and just manipulates them by the rules of complex algebra. But for us writing things down, this is convenient to do. And then we have to do the Fourier transform. So we'll talk more about Fourier transforms later, but here's an expression. We have our signal as a function of time. It's multiplied by a complex exponential as a function of omega, and then integrated from 0 to infinity. This will turn out to be important later. If you look up the standard Fourier transformation in a math textbook, it'll be defined usually from minus infinity to plus infinity, but we don't have any signal at negative time. We have no signal before the pulse. And while that may seem like a trivial difference, it turns out not to be trivial. So we'll come back to it. But in any event, we know the functional form of our simple signal, and we just have to ask Mathematica to do the Fourier transformation. So we get the imaginary part and the dispersive part that I wrote down before. And then here's the spectrum, obviously, again, once again, for the protein ubiquitin. So what can we do with our simple mathematics so far? Right? We basically can use the right-hand rule to rotate magnetization around the Cartesian axes, or we have the matrices that we can multiply the vectors by. So another experiment that we could do is the inversion recovery experiment. So here the signal starts on Z. A 180-degree pulse turns the signal upside down. Now there's no precession, but there'll be T1 relaxation. The magnetization will start to relax back according to the T1. of the signal. So I've just added in the solution to the differential equation from the block equations for T1 relaxation. And then at the end of the period T, we have another pulse that we could imagine as, in the simplest case, as X or Y 90-degree pulse. I did it as an X pulse. So I have magnetization on Z. Now an X pulse, my thumb points along X, my finger's on Z. The magnetization now rotates towards the minus Y axis. And that's what this minus sign here represents. And J is a unit vector along Y, so the minus sign tells me I'm really on minus Y. And now this again will precess around the Z-axis. So magnetization that starts on minus Y, as it starts to rotate, what axis will the magnetization be rotating towards? So now the field is the Z field. Right? The magnetization starts on the minus Y axis. What axis does the magnetization start to rotate towards? Towards X. So when I do the arithmetic, I didn't even bother to do it, but the magnetization will rotate towards the plus X axis. So the part that stays on the minus Z axis will have the cosine omega t trig component, and the X axis will have the sine omega t. When we do the Fourier transformation, compared to our first experiment, the signal will be 90 degrees out of phase. Instead of having cosine on X, we'll have the sine on X. That's a 90-degree phase shift. So the spectrum you would see would be dispersive, but then you dial the knobs on the spectrometer to bring it into phase. And then the signal amplitude then depends on the delay t, and we can plot that to see the inversion recovery. And here's an experiment for, again, for ubiquitin. At time 0, the magnetization is turned upside down. Over time, the signals start to relax. Eventually, they become positive. And then they continue to grow in the positive sense until they would eventually reach Boltzmann equilibrium. And then here's some data for one of the peaks, I think one of these methyl groups. But you can already see something interesting here. Right? If we look here at 1 second, the methyl groups have flipped up. They're positive already. These are the aromatics, and they're still upside down. So we already see that there's some difference in relaxation rates, even in the simple experiment, due to whether a given spin is a methyl group or an aromatic group in the protein. But even the methyl groups, if you look here, and here's these signals here are methyl groups. And you can see that they flip over at different times. Here, this one is still negative, and whereas this one is already flipped. So even the methyl groups, there's some difference, and that's due to some combination of local packing of protons and the dynamics of the molecule affecting the relaxation rates. And then the other experiment we can do is this, with this simple picture, is the spin echo. So now we'll have a 90-degree pulse. If that's X phase, we'll generate minus Y magnetization. The magnetization is going to precess, and then we're going to apply a 180-degree pulse, and then let the magnetization precess again. So the idea now in the pulse sequence is we want to divide the pulse sequence up into pieces and analyze everything piece by piece. So I chose the phase phi 1 to be X. So the magnetization starts on Z. an X pulse, my thumb is along X, the magnetization rotates to the minus Y axis. And that's what I see here. The minus sign tells me I'm on the minus Y axis because J is the unit vector. Now the magnetization starts to precess during the period T over 2. So I'll pick up these trig functions. The part of the magnetization that's on minus Y will be modulated by cosine omega t. And again, minus Y is going to precess towards plus X. So I'll have plus X magnetization. And again, here's what we see. The X magnetization is positive, modulated by sine omega t over 2. And the Y magnetization is negative, modulated by cosine omega t over 2. And of course, there's relaxation. So I just added relaxation on in an ad hoc way. And now I apply the 180-degree pulse. And I'm going to apply the 180-degree pulse to each of these components. The 180-degree pulse I picked is Y pulse. So what will a 180-degree pulse do to X magnetization? So my thumb is on the Y axis. The magnetization is on the plus X axis. And what will a 180-degree pulse do? The magnetization is going to rotate down to minus Z and then all the way up to minus X. A 180-degree rotation around Y of something that starts on X will rotate to minus X. Everybody happy with that? And then, what does a 180-degree Y pulse do to Y magnetization? Doesn't do anything, right? The magnetization and the pulse are along the same axis, so there's no rotation. So nothing happens. I keep minus Y magnetization. And now I'm done with the pulse. So each of these two terms is going to precess again for another period T over 2. These trig factors that came from the first T over 2 are now just mathematical terms. They just come along for the ride. They're unchanged. And I'm just going to now take this minus Y magnetization and re-evolve it. Take this minus X magnetization and evolve it. Take this minus Y magnetization and evolve it. So I'm going to end up with 4 terms, right? Each one of them is going to split, again, into a sine component and a cosine component. I might have gone 2 slides. Yep. So what happens to the minus X magnetization? Well, the minus X magnetization will have a component that goes as cosine omega t over 2, and it's carried along the sine component with it. So this part just carried down, and this was the cosine projection from the second t over 2 period. And minus X magnetization rotates towards which axis? So my thumb is along Z, minus X rotates towards if I draw a little, I can draw a picture here. X, Y, minus X, minus Y. Magnetization on minus X rotates around Z towards minus Y. Right? Z is coming up out of the page. My thumb is up out of the page. Minus X will rotate towards minus Y. And that's what we see here. We have a minus Y term It had one sine component, and now it picks up a second sine component, so I get sine squared. The minus y magnetization was a cosine. It will get another cosine term, so I have cosine squared, but minus y will rotate towards plus x. So I pick up a sine component, and this cosine bit came along with it. So here are my four terms. And now I have to just remember some trig. So two terms cancel, and I end up with minus sine squared minus cosine squared, and I remember that sine squared plus cosine squared is 1. So I end up with magnetization on the minus y-axis, and the signal is now proportional to e to the minus r2 times t. Because the damping went on. The damping wasn't affected at all by the pulse. So we can use this experiment now by varying t to then map out the decay of magnetization to measure R2 in a simple case. But more importantly, this is the first example of using some combination of pulses and delays to modify the signal. This looks like there was no chemical shift evolution during the period t. The magnetization processed for a total period t, but that evolution was refocused by the 180-degree pulse. So in essence, we turned off the chemical shift at the end of the period t, leaving only the relaxation. And almost all of modern NMR revolves around ways of using RF pulses and delays to turn off, or sometimes not completely turn off, but modify the effect of certain magnetic interactions relative to other ones, so that we can take something that would be incredibly complicated problem to solve, an incredibly complicated spectrum to look at, and simplify it by isolating only those parts that we care about in a particular experiment. And in solution, the spin echo underlies 75% of what one does for playing these kinds of tricks. You'll eventually see that many, many complicated solution experiments are just combinations of spin echoes pasted together in various ways. It gets to be a little more complicated in the other 25%, and generally more complicated in solids, but the idea is always the same. We want to try to manipulate what the magnetization is doing by pulses and delays in such a way that in our language we'll say we can refocus certain interactions, or sometimes recouple certain interactions, make them come back when they might otherwise have gone away, make them go away if they're normally there. So this is the first example. Unfortunately, we're pretty much done. Oh, here's again data for ubiquitin. This is the amide region, just for two different delays. So you can see when the delay is short, there's lots of signal. When the delay is long, the signal is relaxed away, and one can estimate then what the R2 is, kind of an average R2 for the amides. And in solution NMR, that's one of the first things one wants to know something about, because if that rate constant is too large, many of the experiments that we would like to do are not going to work, because many solution experiments for bio macromolecules start with amide proton magnetization and then start migrating that magnetization around and then bring it back to the amide proton for detection. So if that magnetization decays too quickly, the experiments will be very low sensitivity. So pretty early on, one wants to have some idea of what that relaxation rate is, even if it's just in kind of an average sense. So one thing you notice here, by the way, is, of course, not every amide has the same resonance frequency. So far, all we've talked about is the Larmor frequency. The Larmor frequency was minus gamma times B naught, and gamma is the same for all hydrogens. It's the same for all nitrogen 15s, the same for all carbon 13s. So something else is going on. Otherwise, all the amide hydrogens would have the same frequency. There would only be one peak. And of course, the very first NMR experiments were done with magnets that were quite inhomogeneous. And it took a little while before the magnets got homogeneous enough that people realized that not every hydrogen had the same frequency. And the first cause of that is the chemical shift. So I'll just introduce this because Anne walked in. And here is a tensor sigma, which is the chemical shift tensor written in its principal axis frame. And I won't say much more about the principal axis frame for quite a while. And in fact, if I'm lucky, I won't say it at all. Anne will talk about it. But in the principal axis frame, you can see that the chemical shift tensor has three components called sigma 1, 1, sigma 2, 2, and sigma 3, 3. The average of those three is called the isotropic chemical shift, and that's what we observe in solution. We observe that in solution because rapid tumbling of the molecule averages all the directions. So if a solution person says chemical shift, they mean the isotropic chemical shift, even though they might not say isotropic. But these three values might not be the same. And we could also define delta sigma, which is called the chemical shift anisotropy. And then eta is called the asymmetry of the tensor. And there's sometimes some tricky things about how the asymmetry gets defined, but again, we can leave that for the future, for a future class. So then we can modify our resonance frequencies just by adding in here this little correction factor, 1 minus sigma iso. The Larmor frequency was just minus gamma times B1. And then we add in this little correction factor. And again, in the interest of getting us going, I'm not going to, at this particular moment, justify my S for right correction factor. Why is it 1 minus gamma? For 1 minus sigma iso, we'll come back to that.
Art,
yep.
Is the microphone important for this recording? Is that why you
Yes.
It's just gone off. You may not be able to hear that. Just now.
Is it back on?
Yes.
Oh. So what we really mean by omega then is this little correction factor added in, and then it also turns out that knowing the absolute size of B naught of the magnetic field isn't very easy. So what we normally do is reference spectra. We don't really talk about the absolute number of megahertz. We reference the NMR spectrum against some reference compound. So down here is an expression then for a reference in which we measure the frequency of some reference compound, and these are now defined by IUPAC. For different nuclei.
Hello? If you're asking a question, can you speak up?
And then we have tables of what we expect for example, for nuclei in proteins or for nucleic acids, etc. So, and then we can also estimate the relaxation rates or the line widths, given that we know something about the size of the protein. We'll come back to this when we talk more about relaxation. But again, these two, in a simple case, in solution, knowing something about the size of the protein and sometimes the shape of the protein can help one estimate in the beginning what you expect for relaxation rates. And if you find relaxation rates that are way too large, that might suggest there's aggregation or dimerization of the sample. And if you have relaxation rates that are way too small, that might suggest the protein is in fact unfolded under your conditions. All right, so what goes wrong? So the first NMR spectra, the signals were basically blobs. The homogeneity of magnets improved. People learned how to build shims or how to shim magnets. And the chemical shift was discovered. And then magnets continued to improve. And suddenly the resonance line split again into multiplets. And then it was figured out that those multiplets were caused by what we now call the scalar coupling. And the scalar coupling is an interaction between pairs of nuclei in which they feel the magnetic effect. One nucleus feels the magnetic effect of the other. And the scalar coupling is relayed through the electrons in the covalent bonds, with some small exceptions we'll leave out for right now. So one talks about, for example, the one bond J scalar coupling, or J, would mean the interaction between two directly bound nuclei, or the three bond coupling, in which case we have two nuclei that are separated by three covalent bonds. And the main effect of the scalar coupling is to slightly modify the energy levels. So if we have two spins, we now have four possible energy levels, because both spins could be in the alpha state. Spin 1 could be alpha and spin 2 could be beta. Spin 1 could be beta, spin 2 could be alpha, or both spins could be alpha. And that's shown here. So here's the alpha-alpha state, alpha-beta, beta-alpha, and beta-beta. We'll, for most of the course, call the two spins I and S. Sometimes we'll use subscripts like I1 and I2. But that can lead to...
I think it's Liz and her husband.
Let's see if it's my phone somehow turning this off. So we'll usually call the two spins I and S. And our usual convention will be that in these kinds of notations, the I spin will be listed first. So these are ordered, so the first element is the I spin, the second one is the S spin. In any event, we can just work out what the energies of each of these are, because the energies are additive. So here are just the energies. if we didn't have this J coupling, we just have the chemical shift.
And then the spectrum we would see
What kind of batteries? Thank you.
Yes, Mike is first.
Yeah, or maybe the staff, but yeah.
well, I'll try to talk loudly in the intro. So this simply then would be the spectrum we would see. We have, we've gotten ahead of ourselves. I've got that. I think I might be missing a slide, but the main idea is that when the scalar coupling interaction is present, the energies are now modified. They're modified by the scalar coupling, which is called J, and it's measured in hertz. And then the two magnetic quantum numbers, the magnetic quantum number of the I spin and the S spin. And then this factor of 2 pi that makes everything in angular units. The effect of that, right, is if both states are alpha, for example, then this would be 1/2 times a half, which is a positive number. If both states are beta, we get -1/2 times -1/2, which also is positive. So the effect of the scalar coupling, if J is positive, and J can be positive or negative, let's assume J is positive, for the alpha state is to move the energy up, and for the beta state to move the energy up. But what happens if one is alpha and one is beta, then this is negative 1/2 times -1/2. And these two energy levels go down. So instead of this energy being identical to this energy, now this energy becomes smaller than this energy. These resonance lines over here that were doubly degenerate now split into pairs of multiples. In essence, if we take a simple case, suppose we have an amide hydrogen, and it's connected to a nitrogen 15. So if this is the hydrogen spectrum, then the energy is slightly different if the N15 is in the alpha state than if the N15 is in the beta state. So one line represents the amide hydrogen magnetization, where the nitrogen 15 is alpha, and the other represents the amide hydrogen magnetization, where the N15 is beta. And the converse would be true over here. This is the nitrogen spectrum. One of these resonances is the nitrogen 15 magnetization, where the amide hydrogen is alpha, and the other one is the nitrogen 15 magnetization, where the amide hydrogen is beta. J coupling, in many experiments it doesn't matter, but when we get to experiments called TROSY, or so-called spin state selective experiments, then it does matter, and people got it wrong, get it wrong in the literature all the time. People meaning me, because if you look at my papers, we change the labels periodically as we think we've done it correctly in some new paper. So the problem that we have is basically this. Once we introduce the J coupling, or in solution, or in solids, the dipole coupling, we then have interactions between pairs of nuclei. And the block picture doesn't include that. So our block picture started assuming we have isolated nuclei. They're not interacting with each other magnetically. And now we see the J coupling is evidence that the nuclei have magnetic interactions. So if we're going to go forward with NMR, we have to figure out how to handle these magnetic interactions between pairs of nuclei. Fortunately, at least as far as I know, and Anne can contradict me, there are, at least in biological NMR, interactions that are important in which triplets or quartets of spins interact. All the non-negligible interactions are pairwise. There can be lots of pairwise interactions. There might be dozens of them, if not hundreds of them, but they're pairwise, and that's a tremendous simplification in the theory. So the question is how to go forward. One peculiar thing that's about to happen is that an NMR experiment is at some level classical. A solution sample typically has of order 10 to the 17th spins in it. That's a very large number. You don't expect, right, quantum effects to be very large in a system with that many particles in it. If you had, okay. Like everything else, most of the time, the size of the quantum effects scale is something like the square root of the number of particles. So by the time you get to 10 to the 17th particles, you don't expect there to be very large quantum effects. And in fact, you've already seen that. I happily said that we could measure the X magnetization and the Y magnetization and treat them as a complex vector and Fourier transform them. But remember, quantum mechanics said I couldn't specify the X and Y components of the angular momentum operator at the same time as the Z component. I can only specify one. So there should have been a Heisenberg uncertainty relationship between the X magnetization and the Y magnetization. But that uncertainty principle is scaled way, way, way down by the square root of the number of particles, so I hardly care about it. But what we're going to do, or start to do next, is use a quantum mechanical theorem or a quantum mechanical formalism called density operator formalism to explain these pairwise interactions in NMR. So it might seem very peculiar to use a quantum theory to describe what is a more or less classical experiment. And in the early days, Robin Mendel argued kind of vociferously against introducing all this complicated quantum mechanics. But it turns out that the quantum mechanics provides so much insight into what's going on that we do it
even though we could probably reformulate the whole problem and sort out what was going on without the quantum mechanics. So it's really all the conceptual insight that we gain by adopting this approach, as opposed to some fundamental need for quantum mechanics in a system of so many particles. So why don't we take a couple-minute break at this point? You can stretch your legs, and we'll come back and talk and just get started then on the quantum mechanics. Of course, the quantum mechanics will be complicated enough that we'll keep coming back to the block picture to keep getting our moorings when we start to get confused. And then at the very end, we'll end up trying to convert the quantum mechanical picture into something that looks very much like the block picture, because we're used to thinking that way. Okay, so 5-minute break.
That depends which way you think you're asking. Not really. Yes. No. No one likes to get up and walk around this. Okay, so the quantum mechanics starts with the Schrodinger equation, just as one might expect. And the Schrodinger equation has h bar in it. And we will assume h bar is equal to 1 most of the time, so we hide h bar.
And that essentially means that we work in units of frequency. So instead of energy, remember energy is h bar times omega. If we say h bar is equal to 1, that's equivalent to say our energies are equal to omega. So we work in frequency units. And of course, that's pretty convenient for us because we're going to do spectroscopy where things show up as frequencies. On the other hand, if we ever need real energies, we can always put the h bars back in by dimensional analysis, make sure we get it back in the right place to generate energies at the end of the day. So we'll write the Schrodinger equation like this with no h bar. So just to remind you, psi here is called the state function or the wave function. That's what we would like to know. If we knew that, we can calculate the properties of the system. And h, the Hamiltonian, contains the physics of the problem. So if we knew what h was, we might hope to solve that differential equation for psi. And then once we knew psi, we could then calculate things we were interested in. Now, h in general is the kinetic energy of the system plus the potential energy. And luckily for us, there's not kinetic energy that we need to think about. We'll just have the various potential energy terms, and these Hamiltonians in NMR will turn out to be very simple. This, in my notation, usually H naught will refer to the Hamiltonian coming from the B naught field. H1, the Hamiltonian corresponding to the B1 field, and then H local, all of these local magnetic interactions that give rise to the chemical shift, the scalar coupling, the dipole coupling. The meaning of psi is given by this expression that the function psi times its complex conjugate.
I'm just getting a little bit of feedback.
Now, we've never figured out what causes that.
Sorry.
The product of the complex conjugate of psi times psi is the probability at some time t that that physical system has a particular configuration described by psi. This implies that a proper wave function has to be such that the integral of this product has to be unity, because probabilities have to add up to 1. Many, many times going forward, we won't worry about that. We may have wave functions that aren't normalized, but we can always normalize them if we want by this expression. This expression down here will serve to normalize. That's just taking whatever the integral was, taking its square root and using that as a normalization factor. So that's trivial. We'll do it when we need to. Frequently, we won't have to bother. The other bit of this is seems to have disappeared. I somehow delete the slide. No, maybe it's just a slide somewhat out of place. So what is this quantity h? So in the quantum mechanics language, h is, h is called an operator. Psi is a function. Psi is a function, maybe very complicated, but it's like the other functions you're used to, like sines, cosines, exponentials, etc. An operator is a mathematical object that transforms one function into another function. A function is something that transforms one number into a different number. If you take pi over 2, sine transforms pi over 2 into 1. You put a number into the function, you get a number out. An operator generalizes that. It takes one function and turns it into a different function. So an operator that you're quite familiar with is differentiation. Differentiation takes the function x squared and turns it into 2x. You put a function in, you get a function out. And that's, in fact, my example. And some operators will have the funny property. For example, here, if we take the derivative of the function e to the lambda x, the derivative of that is lambda times e to the lambda x. And that's equal to lambda times the original function. So in this case, the derivative operator acting on the exponential function gives back the exponential function times some number. And in the language then of mathematics and quantum mechanics, the exponential function is called the eigenfunction of the derivative operator. And we'll be very interested in functions that are eigenfunctions of various operators that come up in quantum mechanics. And in part because, or in NMR spectroscopy, in part because we'll be able to use this simple property to analyze various equations. Now, something seems frozen. So again, to get our feet wet, here's a simple calculation. It should have started on a previous slide. Where did it? Let's just skip that for now. It's out of order. So why do we bother with quantum mechanics at all? And the purpose of quantum mechanics is to calculate some observable, something we could go measure. There's a famous aphorism attributed to Feynman that a graduate student comes up and says, "Professor Feynman, what's the meaning of quantum mechanics?" And he says, "Shut up and calculate." So we want to calculate an NMR spectrum, and so we need a recipe for taking the wave function, what comes out of the Schrodinger equation, and converting it to something we can measure in the lab. And this is the equation here that does it. This says that the expectation value, something we can measure, associated with some operator A, is given by this kind of integral over this sandwich. So we take the integral of the complex conjugate of the wave function times the operator times the wave function, and then integrate over all the relevant variables. And what we end up with is the expectation value. And in quantum mechanics, the expectation value will be the number that we get is the average of making the measurement over and over and over again on an ensemble of identically prepared systems. We'll get around that in the next class, that very specific result. But this is our recipe. So if we know the Hamiltonian, we can hope to solve the Schrodinger equation for the wave function. And then you tell me you want to measure voltage. I go ask a physicist what operator A is associated with voltage. and I put that operator in here with the wave function, and what I get out of the calculation is the voltage I would measure in the laboratory. We want to measure NMR spectra, so eventually we have to know what the operator A is that's associated with the NMR signal. If we know that operator, and we're able to solve for the wave function, we can then calculate the NMR spectrum. This thing in the brackets would become the free induction decay. Now, it turns out that some operators have the property, another property that they're called Hermitian. A Hermitian operator has the property that it's equal to its own Hermitian conjugate, which sounds like a tautology. The Hermitian conjugate is the transpose of the complex conjugate, and it'll probably be next class that we'll talk about what the transpose of an operator looks like. But the important thing about Hermitian operators is that their eigenvalues, these constants of proportionality that come out of the action of their eigenoperator on them, are real numbers. And remember, everything we measure in the laboratory is real. We don't measure imaginary numbers in the lab. Voltage is a real number. So that means that operators associated with observable quantities have to be Hermitian operators because they have to have real eigenvalues. And that limits, in fact, that ends up limiting ourselves to all of quantum mechanics is essentially about Hermitian operators, which turns out to be a simplification. So, are things changing here? The question is whether to start all of this. I think we won't start all this today. We'll leave that as the stopping point for today's lecture because the next chunk is a lot of algebra. So I don't think I should start a lot of algebra at 2:30. But you might want to look. Mike will get the notes posted. He's at the other side of a very bad internet connection right now. But he'll get the notes for today's class posted so you can look ahead, hopefully, for tomorrow's class when we'll do a lot of algebra. So, questions? So we'll do probably a little bit of problem set tomorrow, but the rest of it really next week. We'll just get started tomorrow.
Hi, Dory. unfortunately, I'd rather talk today or tomorrow. Do you think you can make those small changes?
So one way of thinking about the,
I know sometimes when you just have preliminary data, it's
oh, I gotta stop the Bluetooth.
it feels weird to plug. Just do it, just do it. Okay. Yeah. How you doing?
In the